Purpose of this lab was to examine the motion of a two-dimensional spring mass system where the mass swings in an arc while oscillating on the spring. After collecting data from Tracker and the computational model, I concluded that the energy principle for the spring mass system holds true and the motion can be predicted by using Newton's second law. For the beginning part of my lab, I imported the video into Tracker, and I set the mass and collaboration stick and the coordinate axes to what was specified. And then I played the video and recorded the center of match during each frame. And from the data I collected in here, I exported into a spreadsheet, which I opened with in Python code to compare the data from the x and the y coordinates with that of the computational model. In addition to using the force formulas in Newton's second law to solve for the new position and the new velocity, and the forces being the force of gravity and the force of the spring constant, and getting the net force to solve for the velocity and the position, we include energy formulas in the Python code to test whether or not the energy principle holds true. We have kinetic energy equaling 1/2 the mass times velocity squared, the potential gravitational energy equaling mass times gravity times height, or mass times gravity times y, in this case as y represents height. And we have the spring potential energy, which is 1/2 the spring constant times the stretch. And the energy principle holds true if the sum of the energies in each time step is equal to 0, showing that energy is being conserved while the energies are changing. Here's the Python code, and I set the ball's mass to equal what was given, and we have the ball's initial position vector, which is the initial x and y coordinate of what was taken in Tracker. We have the gravitation constant, which is equal to 9.8. We have the spring constant, which was given to us in the video, and we have the stretch of the spring as it is at equilibrium, which is also given at the video, to equal 0.123. And here we update the spring, well, not update, but we set the initial conditions of the spring, where the max stretch is the ball's position minus the spring position, which is vector 0, 0, 0, which is what we set the origin of our axis to be in Tracker. And then we solve for L hat, which is the direction, which would be the direction that we'd use to computate for the spring force. And we solve for the stretch, which is the magnitude of L minus the stretch at equilibrium. And here we plug in the force equations that we had before, that I just shown you previously, to solve for the initial energies. And here we logically set the initial energies to the final energies of that in the previous time step. And we solve the forces here using the force of gravity formula and putting that in the y direction, in the y coordinate, because it's going down. And the force of the spring times the L hat to give that direction. And we have F net, and then we solve for the ball's position and the ball's velocity using Newton's second law, where the ball's velocity plus the F net divided by the ball's mass times delta t is the ball's velocity. And the ball's new position is the ball's initial position plus the ball's velocity times delta t. And here we just update the spring using the same equations that we used up here for the initial conditions. And here we calculate and update the new energies using the same equations as shown before. And if we run this, we have this is the x coordinate and this is the y coordinate. The model is the blue line, which as you can see is pretty steady. and the tracker, the one I recorded in tracker, is red, which, as you can see, starts to slowly fall behind the model's prediction. And in here we have the y coordinates, which the green is the model, and the yellow is the tracker. And as you can see, the amplitude does not fully go all the way down to where the computational model is. And the reason for these discrepancies, I believe, is human error and the fact that we have not added drag force in the computational model, which would slow the system down and change its position. And here we have a graph of the energies. And right here, the green represents the gravitational potential, and the red represents the spring potential, and the blue represents the kinetic energy. And as you can see, the yellow line represents the total energy of the system, and seeing that it's zero consistently throughout the entire graph, the entire time, it's safe to say that the energy principle does hold true for this spring mass system. And for the last what if, what does it mean question, we had to calculate the two separate estimates of the oscillation periods for the x and y data. They are different because we had to use different equations. For the y data, we used gravity, and here in the x data, we used k, m and k. And for the y data, it turned out to be 1.3 seconds, and for the x data, it turned out to be 1.5 seconds.